Hi, I'm Dr. M. Geetha, working as professor in the Department of Information Technology, SA Engineering College, Chennai. Today we are going to see about asymptotic notations in design and analysis of algorithms. Under this topic, we are going to see first introduction to analysis of algorithms, then asymptotic notations used in various algorithms. Let us start with some terminology. The first terminology is computational problem. What do you mean by computational problem is if you can able to write an algorithm for a problem or if you can able to design a model for any problem, then the problem is said to be computational problem. So the next terminology is an algorithm. We know that algorithm can be defined as a set of instructions that need to be followed to solve a particular problem. So the third one is a good algorithm. There can be many algorithms for a particular problem. So what we want to do is we have to select or classify an algorithm to be a good one. Let us understand the properties of good algorithm. The first property is correctness. An algorithm is said to be correct if for every set of input it holds with the correct output. So what we are expecting, it has to produce. Then the next property is finiteness. The algorithm must always terminate after a finite number of steps. So which means that it should not go into the infinite loop. The third one is efficiency. It depends on two parameters. One is computational time, another one is memory. The computational time, the time taken to generate an output corresponding to a particular input should be as less as possible. And the memory also should be as less as possible. We have to use it. Then the So the last terminology is algorithm efficiency. Already I told you that there are two parameters available here. One is space complexity, another one is time complexity. Space complexity of an algorithm denotes the total space used by the algorithm for its working for a various input size. The time complexity is the number of operations of an algorithm to complete its task with respect to the various input size. So while considering algorithm efficiency, we have to take care of two parameters. One is space complexity, another one is time complexity. So far we have covered the terminologies, computational problem and algorithm, a good algorithm, finally efficiency of algorithm. Now let us move on to the subtopic asymptotic notation. Here we need some standard notations to analyze the algorithm. We are going to use big O notation, big omega notation and big theta notation. Let us start with the big O notation. The big O notation defines the upper bound of an algorithm. That is, our algorithm cannot take more time than what we are specifying here. In other words, we can say it as big O notation denotes the maximum time taken by the algorithm, or simply we can say it as this is a worst case time complexity of an algorithm. Then the next one is how to write this representation. For that case, we have to compare our algorithm G of n with the existing algorithm F of n. Always, already I told you no, which is the upper bound of an algorithm. So always our function G of n is greater than or equal to F of n. So see the graph. Here G of n is our algorithm, F of n is an existing algorithm. See the graph line. This G of n is always greater than the F of n with respect to the constant. So this is the representation of G of n. So how to represent this big O notation is F of n which is equal to big O of G of n. So the next notation is big omega. It denotes the lower bound of an algorithm, that is time taken by the algorithm cannot be lower than the time what we are specifying here. In other words, this is the fastest time in which the algorithm will return a result. We can write it as always which is less than or equal to the existing function f of n. In graphically, see the diagram, always which is lesser than the existing function f of n. So f of n equal to big omega of g of n. So the last notation is big theta. which is used to find the average bound of an algorithm. That is, it defines an upper bound and a lower bound, and our algorithm here lie between the levels of upper and lower. In diagrammatically, how to represent this notation is f of n, which is equal to theta of g of n. See the diagram, it will go in between the levels of c1 g of n and c2 g of n. So for notations are over. Here I am going to relate notations with different cases of analysis of algorithms. I can relate omega with best case because it provides lower bound, and big O with worst case, already I told you, because it provides upper bound. So the middle case, big theta with average case. Using this we can find out the average time of an algorithm, what will be taking as a running time. Then the next let us see one example here. I have taken linear search as an example. In this searching algorithm, we are finding whether the element k is present or not. If the element k is present in an array, which will return 1 to you, or otherwise 0 to you. Next, we will move on to analysis of this algorithm. Here we have three different cases. In best case analysis, it provides lower bound of an algorithm. In worst case analysis, it provides upper bound of an algorithm. In average case, in between these two levels, we will be getting as time complexity. There are two options available. One is item present in the list. Another one is item is not present in the list. Consider the first case, item is present. In the best case analysis, we will be getting big O of 1 will be the time complexity, and worst case analysis will be getting big O of n as time complexity. In the average case, we'll be getting big O of n as the time complexity of analysis of this algorithm. Why this is big O of n again is average of two levels, 1 and n will be the 1 plus n by 2. We have to ignore the constant as well as the denominator value. We'll be getting again O of n will be the time complexity. Then consider the next case, item is not present in the list. For the case of not present, all the cases you will be getting big O of n will be the time complexity. Why this is big O of n is we have to go through all the elements, then only we will be knowing that element is not present in the list, so that the all the elements can be given by n. So the time complexity of all the cases will be big O of n. So up to this we have covered the time complexity of linear search algorithm. So in this class I have covered the terminologies which have been used in design and analysis of algorithms, and also the asymptotic notations used for denoting the analysis of algorithm. Thank you.